So here I am talking about lecture number 13, and here we will discuss about function of discrete random variable. So once we are having a discrete random variable, then can we define other random variable based on some composition mapping kind of approach? So what will happen if you are defining function of a random variable that again happens to be a random variable due to that composition approach, because the random variable, but it is a function from sample space to R, and over that random variable we are defining a new function, and hence we can say that the new function would be a composition function over, and you can go back to the sample space. So that's where if you take any function of a random variable, that always define a random variable over the same sample space. Okay, that is the, so all these are just simplification, because we are till now we have already seen very limited number of discrete random variable, and if you talk about data collection, most of data, if you try to apply some kind of machine learning algorithm, what is happening that always we take discrete data, then we say that data is coming from some distribution, but we don't know from what is the source of that data, what is the source distribution of that data. So what will happen, just till now we have gone through limited number of discrete random variable. Can we talk about further random variable? Yeah, we can talk by introducing function of random variable. So that's why function of random variable is very important in order to just extend the idea that there would be various sources of whatever sample data you are taking, there might be various sources, so you need to know that. Okay, so before going to discuss that, I will coming to outline. In this outline, in this lecture, first I would talk about last class. In last class I had discussed that the relation between binomial random variable and Poisson random variable. I had told that when you are talking about some kind of counting principle, counting of success, how many success you count out of several trials. If you observe n number of trials, in n number of trial you try to count k success. Suppose k success, then by default n minus k would be failure. Okay, am I audible? Anyone respond, am I audible or not? Okay, thank you. I'm talking here. We are having n trial. In n trial, uh, suppose we are talking about there are k successes, so by default n minus k failure would be there. So if you try to model this problem, you can model with the help of a binomial random variable. The corresponding PMF would be a binomial probability kind of thing. So binomial random variable would come here. Okay, so if you, I had already mentioned that suppose n is very large, and definitely one more parameter would be there here, that probability of success. So probability p, the probability of each success, that means whether you define success, what is your way of defining success in that particular probabilistic model, whether it is a getting head or getting pass or something like that, it depends upon the problem. Okay, so suppose n is very large, and in that case, if a number of trial happens to be very large, p would be also, we are assuming that p is very small, then in that case, if you are just applying binomial random variable or binomial, try to calculate through binomial probability distribution, then you will face computational issue, because a small number you have to, n is very large, and here the corresponding binomial uh, probability happens to be like this way, p to the power k into 1 minus p to the power n minus k. This, apart from that, we observe the coefficient, that means out of n trial how many success of size k we observe. So that's where this coefficient, binomial coefficient n choose k is coming. So if p is very large and, sorry, n is very large and p is very small, and I am asking to compute this binomial probability, then definitely computational would be very tedious. So what we do here, I will talk about the same computation you can approximate by Poisson distribution. But Poisson distribution also counting number of success in a particular interval. So there would be one additional term in Poisson distribution. What we observe? We observe one interval. So in particular interval or particular space, we try to calculate number of success of something. And in the Poisson distribution, we are having n is very large and p is very small. But in binomial, generally, when we are applying binomial, when n is it is not much large, like a simple mediate, it might be 10, 20 something, 50 kind of things, and p is appropriate around 0.5, 0.6 something like that. It is not like that very less than 0.001 something like, no, not like that. So p is just moderate, you can say that. N and p both are moderate, then we can go for directly binomial. And so simply binomial, random variable model, simple kind of things, like a number of tossing. When you're tossing a coin 10 times, 15 times, 50 times, 100 times, then you are free to go for binomial. There is no issue, because p would be there. If coin happens to be a fair coin, then p would be 0.5, and calculation would be very simple, you can easily calculate. But if you are taking very unbiased coin, then situation would be very problem. There would be definitely some kind of issue would be there, probabilistic, some kind of issue. What kind of problem will come, that when you are counting number of buses passing through one bus stop in a given interval, so definitely you will face problem when you try to model that with the help of binomial. So you have to go with Poisson distribution. That thing I will discuss. So in short, I would like to say that I would like to approximate binomial distribution with the help of Poisson distribution. So that is the, and next I will talk about function of random discrete random variable, or simply function of random variable I will talk here. And at last I will discuss about expectation and expected value of a random variable. So expected value also, again, I can say that it is highly dependent on the function of discrete random variable. So those things we will discuss in detail, and these are having a lot of application later. So coming to that, we want to approximate binomial random variable or binomial distribution with the help of exponents or Poisson distribution. How we can do that? So here, the Poisson distribution, I had already defined that Poisson distribution is always dealing with one parameter lambda. There is a single parameter lambda. So the Poisson probability mass function with parameter lambda, it is a good approximation for a binomial probability mass function with parameter n and p. And here, what is the relation between n and p? It would be given by np. And later you will come to see that if you take np in case of binomial, because I haven't introduced expectation and variance, so that's why I haven't discussed about what is meaning of np. Actually, np is suppose x is your binomial random variable with n number of trials and with probability of success p, then np would be expectation of that, expectation of that binomial random variable, or average. Also you can say that average. Okay, so this average, if you try to compare with Poisson distribution, so generally lambda is also talking about average outcome, average number of outcome. Also it is talking about average number of outcome. So you can compare with binomial distribution with Poisson distribution, like by taking this equality, that lambda happens to be equal to n times p. And here, when we approximate a binomial distribution by Poisson, when n happens to be very large and p happens to be very small. So these are the situations when we introduce some interval kind of thing. Like if you are using cell phone, then you can count number of call drops. So call drop, that one is not a frequent kind of thing. So rarely that happens. So you can say that probability of happening of any kind of call drop, that would be a rare kind of probability, very small probability. But again, generally number of call drop, that call drop happens with very small probability. But definitely call drop, if you take a longer duration, then that means number of count would be large. In that process, number of count large. So you can relate lambda with np, just multiply it np, so lambda equal to np, you can get it. So this is the association. Now we try to see approximation. So this is our what, this is our binomial distribution of the number of counts, number of success, number of whatever you count. So this is talking about binomial pmf or binomial distribution. You can say that it is what, nc k, n choose k e to the power k into 1 minus e to the power n minus k. That same thing is 1 minus p to the power n minus k. What is name of this one? We had given name to this one. This one is actually binomial pmf. That means probability mass function of binomial random variable. So in short I'm writing it bpmf. Okay. Now if you see this situation that n is very large and p is very small, then this calculation would be very tedious. So what you do, you can approximate this by, this is in left hand side, it is a Poisson distribution. It is what, probability mass function. That means in the interval of there would be some given interval. In that interval you observe k success, and probability of that success is very small. So in that situation, this one is talking about Poisson distribution. So we approximate this one by this binomial by this Poisson distribution. You can write it p dot pmf. So this result is not a tedious, you can verify it easily. What you do by taking this one, so substitute what you do. So in right hand side you have already expanded form of binomial probability mass function. In right hand side, so substitute in place of this where you replace p, simply p. You don't want to see p in the Poisson probability mass function. You don't observe p. So what you do, you don't want to see p. So here you substitute p equal to, it would be what, lambda by n here. And after that this quantity will take one special expression that would be in term of lambda and p and k. And after that you take limit n tends to infinity, take limit n tends to infinity. Easily you will see that this will be turned into in this exponential form. It will be turned, take n tends to infinity, and after that easily you can get this form. So it is all about approximation of this one by asymptotic approximation. You can say that asymptotic approximation of a binomial distribution by Poisson distribution. Asymptotic means when n tends to infinity. That is meaning of asymptotic approximation. Okay, so I will take one example. Suppose we are having n number 100 trials, and probability of success is very small, that means 0.01. Then suppose we are having a question that we have to find the probability of first 5 success. What is the probability of 5 successes in n number 100 trial? So we have to calculate it. Simply it is what, it can be described by a binomial random variable. So using binomial probability mass function, formula would be given by this one. Just use this formula and just simplify this expression. And after simplification, definitely what kind of in this factorial 100 you can calculate with the help of calculator. This one also calculate with the help of calculator. This one also calculate with the help of calculator. But all these are taking time. These are taking some computation is not just with one click. All these are taking time. Okay, this one again you have to find the power of 0.01. Then here 0.99 will come to the power 95. So all this calculation, if you try to look from computational perspective, that how much time it is taking, that definitely this computation will take time. You can observe that, you can notice to do calculation in calculator, and you can notice that. And that probability is coming how much, 0.0029, very less probability. Okay, but same thing we can approximate it by Poisson. How? So here we don't need n and p. What we need parameter lambda. Lambda happens to be what, it is actually, it is talking about average outcome, average numbers of outcome. So you can simply say that average from the binomial, we will see that binomial, what is the average or expectation of binomial random variable. That one is np. So take define lambda as a product of n into p, and if you simplify, it is coming equal to 1. Very ideal number, very nice number. So using, we are having lambda, just we need lambda, and how many successes it is talking about? 5 successes. So we need lambda and we need k, and substitute this value in the Poisson probability mass function. So just we have to calculate e to the power -1 and factorial 5. These two things we have to calculate and simplify using calculator. You can simplify, you will get this value. This value you will get. You can see that this value and this value is very near to each other. So here you are, with very less computation, you can calculate probability of desired probability using Poisson distribution in place of binomial distribution. So here it is all about saving computational time. So that's why Poisson distribution happens to be very fast. And remember that in case when n is very large and p is very small, I am talking about only in that case, not in every case. Okay, so now next part of lecture, I will talk about function of random variable. So these are demand to discuss about function of random variable. What is happening that I will talk about one motivation first. So consider that you are having a probabilistic model for weather, today's weather, and let the random variable x be the temperature. That one is in, we measure in Celsius. So definitely, if you go weather modeling, always that one is not deterministic. Always that happens to be in probabilistic manner. We can't say that with 100% that weather would be that just after certain time, or that just we can predict something with some probability. So weather is very much uncertain event. You can say that if you try to observe experiment of weather, today's weather, that one is an experiment probabilistic in nature. So okay, so here we are defining a random variable that temperature is a random variable and we do measure in Celsius. Okay, so where function of random variable is coming, you will see that, and we can define, we want to convert that measurement in Celsius into Fahrenheit. So you might be aware of that those two unit of temperature, that Celsius and Fahrenheit. Generally, people are saying that if someone is having fever, that means reading is 100 or 100 not. So 102 or something, 102 or something like that. So what is the meaning of those things? Actually, those are actually in Fahrenheit. If you want to convert same thing in Celsius, it would be around 35 something. Okay, so that's way. What conversion is there? This conversion from Celsius to Fahrenheit is this linear conversion. That means just x is measure in Celsius, multiply with factor 1.8 and add 32. So that will give you Fahrenheit. Just simple linear. This one is a linear transformation. So always when you convert temperature measure in Celsius to Fahrenheit, you can apply this linear transformation. And what we see it here, we can say that it is a here this measure in Fahrenheit, it is a linear function of measure in Celsius, linear function, and later we can go for further non-linear kind of things. How? So for example, if you wish to suppose temperature is very high or very low. So if you such scenario is coming to us, so in order to give a better representation, we go to convert that measurement into logarithmic scale. So in that case, we are defining a function that g of x log x. So y equal to log x. So we are saying, because to make computation easy, we have to convert a small, very small or very big thing into logarithmic scale, just to make calculation simpler. Okay, so here what we observe, so we are having another function of the same random variable x as a temperature. That function is non-linear. Here logarithmic function is what? It is non-linear in nature. You can see the plot. So what would you plot? it is something like that, nonlinear in nature. Okay, so x, take x, this one is x, and g of x. So definitely various function you can observe. Once you are having one random variable and you try to get information measurement from your interest and try to introduce some kind of simplification, you have to come up with some kind of function. So that's why we are talking about the function of random variable. So I will talk about if uh, I simply told that if x is a random variable, then just define a function of that. That would be again a random variable. So if y equal to g of x is a function of a random variable, then y is also a random variable since it assigns a numerical value for each possible event. Why? Again, you can see the same composition approach that random variables x is a mapping from, simply I will take up to range. Here, not r, I will take range of the corresponding random variable x, and afterward we are defining g from where? G from to r. So you can easily say that what g is a function of x. So if I talk about what is the range of g of x that in composition, this O is talking about composition operator. It is simply what? It is a function from sample space to R, and hence we can say that this y equal to g of x, g of x, again what is g of x is same thing, this one. So that's why it is, if you apply here over this one over argument of what outcome omega, so what would be this uh, all these are part of composition function, you might be aware. You are applying over outcome omega. So it would what? Outcome omega will go inside and it will give what? It will give your uh, this y of omega. You can simply call it y of omega. So this is the approach that I try to link with the simple space. So it is just one composition mapping. So that's why we can say that what is the domain of y in total? You can say that every element of every outcome of the sample of space can be engaged by some value of y. Every outcome. It is not like that you are leaving any outcome under the map of y. So, no, it is not like. So every outcome of sample space would it must be engaged by y. So that's why y is also a random variable. Okay. Now I will take one example. So because every outcome in the sample space, it defines a numerical value for x, and hence numerical value y, we can say that also y equal to, so what we do, so take every y, if you take any observe y, observe any value small y, that would be just image of some value of x, definitely image of some value of x. Same thing what I had told that. So we need to obtain the distribution of y. So first, what would be distribution of y? So distribution of y, it will be borrowed from distribution of x. How? We will see it. So to obtain probability mass function for y, and that means value of p y for any y, we add the probability of all values of x, those has been mapped to y. That means we try add the probability of all pre-images of y, then we will get probability of x. So we do calculation like this way. So we are trying to find probability mass function for y, then we again go directly to definition of probability mass function. How it is defined? It is in this function is defined by this probability, that probability that y is taking value y, a small y, that y is observing one a small value y. And what is y? This y is now fixed. Once we observing, we are saying that y is observing this value, it is fixed. So that's why and it is what? It is function of this capital Y is function of x, so we write like this way, and this one is not considered as an inverse function. This one is talking about all inverse images of a small y. That means all the x which has been mapped to y. And if we are trying to find probability of the event that all those x which has been mapped to y, that means we have to sum those probability, and that is giving value of probability mass function for that specific y. So this one is, it is not that we are running over every value of x. We are running here this summation over only x which are pre-images of this y, this particular y. So this is, it is not giving, it won't satisfy normalizing condition. So it would be definitely, this value would be positive, definitely it would be positive, but it would be strictly less than 1. Now we are taking one example. Suppose we are having a random variable x with uniform probability mass function 1 by n. That means x is taking 9 value starting from -4. It is going up to 4. So it is, x is here integer distributed. So taking observing value -4, -3, -2, -1, 0, symmetric about origin 4. Okay, each one is equally likely. So 1 by 9 is probability here. So afterward, we are defining a new function of x. That one is mod of x. Y is a mod of x. Then our question is that what would be probability mass function of y? X is a discrete random variable, and hence we can say that y is also a discrete random variable. Now tell me, and anyone can say that what are the possible value of y? Y, what kind of value y is observing? Anyone? Anyone would like to? I told that x is given with this distribution probability mass function, and x is observing these 9 values: -3, -4, -2, -1, 0, 1, 2, 3, 4. Now tell me what kind of value y will observe. Now y we are defining as a function of x, that one is mod x. Then just anyone try to answer it. It is very simple kind of function. So what kind of value y is observing? Whether my question is audible or not? Anyone try to respond it? Tell me what kind of value y is observing. It is very simple question. Y is mod of x. So definitely, yeah, very nice. So y is observing 0, 1, 2, 3, 4. Only 5 value. So y is observing only 5 value. Number of values has been decreased from 9 to 5. So definitely y will have different distribution. Y, that means y will have different probability mass function. So how we can calculate? How you can calculate? So calculation is very simple. So here you observe that 0, what are the pre-images of 0? If you see in plot, so suppose this is x value, x is taking value 0, 1, 2, 3, 4, -1, -2, -3, -4. And here under this map mod x, here 0 has been mapped to 0, 1 and -1. both has been mapped to 1, 2 and minus 2. Both has been mapped to 2. 3 and minus 3 has been mapped to 3, and 4 and 4 and minus 4 both has been mapped to 4. So what we observe that 0 is having y equal to 0 is having only one preimage. So probability of y for probability mass function for value y equal to 0, it can be given by this single probability. And what is the probability? That 1 by 9. Now in order to calculate other values, that what are the images of preimages of 1? Minus 1 and 1. And hence if you are willing to calculate probability mass function for y equal to 1, so it would be what? Sum of the probability of corresponding preimages. That means one preimage is minus 1. So here remember that suffix here I am giving y, and here I am giving x, so that you have to focus. Suffix here x. So probability of x equal to minus 1 plus probability of x equal to 1, and that x equal to 1, and that will sum to 1 by 9 plus 1 by 9, that means 2 by 9. Similarly you can calculate probability that y equal to 2, that would be also what? 1 by 9 plus 1 by 9, 2 by 9. So for y equal to 1, 2, 3, the probability mass function is taking value 2 by 9, and for y equal to 0, probability mass function for y is taking value 1 by 9. So this is the distribution of y. So from the distribution of x you can get the distribution of y once you know. So that means if you are defining function of random variable, that means corresponding to that random variable you must know what are the value of random variable and what is the distribution. So both things must be clear to you, then you can define function of random variable. I will take another example, and with plot you can see for the last example plot you can see that. So this is the plot of random variable x, and this is the plot for random variable y equal to mod x. So you can easily see that 0 has been mapped to 0, and 1 has been mapped to 1, minus 1 also has been mapped to 1, and the distribution is changed. So this distribution, if you talk about distribution of x, every value of x is taking same probability, and hence this distribution is uniform in nature. So this distribution we are calling it uniform distribution. Here every value of x is taking equal probability, equally likely. But if you observe in right hand side, by introducing this function, the distribution has been changed. It is no more uniform, not uniform, it is different, not uniform. So definitely if you define function of a random variable, the distribution of function of a random variable, it will change, and that change can be measured by Jacobian. When I will talk about in continuous random variable, that change will be measured by Jacobian. One Jacobian factor would come. So Jacobian of transformation, what kind of transformation or what kind of function you are applying over a existing random variable. I will take one more example, x square. So x, we have already given that x is a random variable, uniform random variable with probability, uniform probability 1 by 9. Okay, and x is taking value 9 value between minus 4 to 4 as integer. Okay, and over that we are defining function x square. So possible value of y would be what? That possible value of x square would be 0. A square of 0 is what? 0. A square of 1 is 1, and minus 1 both would be mapped to 1. A square of 2 and minus 2 both would be mapped to 4. A square of 3 and minus 3 both would be mapped to 9. A square of minus 4 and 4 both would be mapped to 16. So that means again this y as a function of x square, it is taking 5 observed value. So and hence we can say that the distribution of y would be different from what distribution x had. So this is the distribution of y. Therefore x equal to, y equal to 0, probability mass function is 1 by 9, and for other value 1, 4, 9, 16, probability mass function is 2 by 9. Distribution looks similar to what mod of x, but y is observing different kind of value other than mod x. because function is different. That's why. Now next I will talk about expectation of a random variable. So we know that random variable is observing various value. So among the various value, we need to find a representative. So what would be representative? That representative value would be given by expectation of that random variable or mean of that random variable. So if you are having various random variable, then among the various random variable, it is not a wise thing to proceed with all those random variable, all those values. What you do, always you want to find a representation, like if you talk about in parliament or legislative assembly, then what we observe that uh, uh, there happens to be people representative. That means MLA, MP, those are what people representative. They represent people of their area. So what you can simply that you have to single out one person as a representative. That representative what some kind of central measure or expectation or mean, you can say that. If someone want to infer something about a particular uh, constituency, particular region, he will he or she will take just a study about that MP, member of parliament, or MLA, and after that he can infer that from that region person might be of that type. That person may have language. Those person may have that kind of language or something like that. So representation, one representation, we try to find it out like that. So here going further, to define expectation. So the probability mass function of a random variable provides the distribution or probability of all the possible value of a random variable. So it is not a single out definition, probability mass function. We need to go for a unified definition, single representative definition. So we summarize this information in a single representative number, such as we call it mean or expectation, and we define the mean or expectation of a random variable. How we define? Because x is a discrete random variable, so we multiply each value of the random variable with corresponding probability or weight and sum it up for all the value of x. So this one is talking about representative number, that it represent the all possible value of random variable. So this representation, this definition, you can say that expectation of a random variable, you can say that it is a weighted average of all possible value of random variable x. So weighted means weight is given by the corresponding probability. That probability, that generally in layman way, also we are very much aware of that what kind of weight we want to assign with respect to that. If someone is very strong, we used to give more weight. It is not like that what that physical quantity weight I am talking about. Weight is some kind of measure, some kind of strength, some kind of intensity associated with each value of random variable. So that is, weight is very general kind of word, you can say that. So in general, if you come in probability, weight is your probability of. So if you are having x is observing one random variable, then x is having some certain kind of probability, some amount of probability, some probability of existence of that value. So that probability we will call it weight of that value. Okay, so consider two. I'm taking one example here. Example one, consider two independent tosses. Okay, so we are having two toss. So each with a 3 by 4 probability of head. That means probability of success is what? 3 by 4. So that definitely this the coin would be biased coin. I am talking about a biased coin. It is not an unbiased coin. Now here we are introducing a random variable x. That one is counting number of heads. So definitely we can say that x is a binomial random variable. Now if x is a binomial random variable, then we are having probability distribution for that, or probability mass function for that. Now question is coming that we have to find the expectation of that x. That means the representative element or average value or mean value. How we can find? So here first, before going to find it out, we have to see that what value x is observing here, and what are the corresponding probability mass function. Those things are very much essential. So x is counting number of heads into two tosses. So x will observe three value. X will take either 0, x will take either 1. That means either 0 head, that means no head, or 1 head, or 2 head. So x is observing these three value. So now next, if x is observing these three value, what are the probability mass function? So in order to know probability mass function, we have to account first what are the parameter here involved. So one is number of toss, that one is 2, and what is the probability of success? 3 by 4. So both things are given here. So easily we can define probability mass function for this binomial random variable. What is probability mass function? When k equal to 0, that means it is associated with in the both tosses we are getting tail. So what is the probability of getting tail? A single tail. That one is 1 by 4, and this one is probability of getting a tail in the second toss, and both happen jointly. Outcome is here what? Order pair. It is sequence of two tuple kind of things. You can say that head tail kind of head tail like tail. So tuple kind of things are coming here. Outcomes are like that. So we can find probability mass function for this binomial random variable. For k equal to 0, it is 1 by 16. For k equal to 1, that means one head. So there are two possibility of getting such value k equal to 1. One is head tail, another one would be tail head. So you have to sum, these two are mutually exclusive, so you have to sum it up, and that's what 2 times 1 by 4 into 3 by 4, and that means this is the probability of value of probability mass function for k equal to 1, and this is the value of probability mass function for k equal to 2. So in total, this one is the probability mass function of the corresponding binomial random variable. So we are having probability mass function. Next we are going to calculate expectation. So how we calculate? So we multiply the value of random variable, random variable, with the corresponding weight. What is the weight? The corresponding weight is given by the probability. So 0 is occurring with probability 1 by 16. So 0 times 1 by 16. 1 is occurring with probability 6 by 16. So that's why 1 times 16. And 2 is occurring with probability 9 by 16. So all these sum it up this expression, and finally you are getting 3 by 2. So this expected value is 3 by 2 for this binomial random variable. Okay. Now we can talk further from that general perspective. I told that probability mass function is talking about weight. So consider we are having a bar or some kind of rod having weight, some kind of weight. That probability is defining here weight, and place at point x. Those are observed value of random variable. Then what is the physical meaning of this expectation? Then physical meaning of this expectation is talking about the center of gravity. Center of gravity, that means a centered point, you can say that. So if you try to apply some kind of torque, those points will move around, always move around center of gravity. So that center of gravity, suppose it is C, then how you can come to know what is center of gravity? Actually this you can get through expectation. And we know that at center of gravity, the sum of torque from the weights to its left must be equal to the sum of the torque from the right, and hence we can say that total torque would be 0, because it is in balance situation. We don't observe any motion, so it is in balance situation, and hence total torque would be 0. And if you simplify it, you are getting that center of gravity, it is actually expectation. It is what? Expectation. If you try to see in picture, you can see like this way. So one weight is here, one observed value of x is here, one observed value here, one observed value here, one observed value here. So each observed value is having certain weight. So all these are weight. And if you try to find it out, where then, if such a scenario is happening here, where is the center of gravity? Center of gravity, definitely it would be in the middle. So how you can design middle? By finding expectation, or by finding the point where torque is 0 in physical sense. Okay, so going further, I will talk about one more thing, that expected value of a random variable. So till now we had already seen that function of random variable. Now, and function of random variable is again a new random variable. The y is a new random variable. variable, then can we find expectation of this new random variable? So if you are finding expectation of this random variable, then there would be two approach. One approach is that what you do, find the distribution of y from the distribution of x and apply the definition of expectation. That means sum the uh, value of product of y with corresponding probability mass function py, okay, and run it over all the observed value of y. This one is one approach that here it is a little bit tedious. Another simplest approach is expected value approach. What you do, you don't need to go to find distribution of y. You can just deal with distribution of x itself, because x is given, that's why distribution of x is also given. So what you do here, in place of y, we know that y is a function of x. So in place of y, we will write it g of x function of y, and we will take corresponding probability of probability mass function of x, because x is dealing here, and we have to run over all the value of x's. It will also give the expectation of x. But this approach, when you find this is simply expectation of y, expectation that from it is directly coming from definition. But when we are finding here, it is not involving the distribution of y or probability mass function of y, so it is an indirect calculation. This we are calling it expected rule, expected. So here indirect approach, and this here we don't need to find the distribution of y, and this calculation, it would look simple. In next class I will discuss the derivation, how it is coming, and I will take few example as well. Regarding attendance and other thing, just it attendance, mark your roll number there in comment box.